carbon, a carbon core in crystalline form. So anyway, it's about 300 times Earth's mass, 5 times Earth's radius. So this diamond composition, if we wanted to convert this into actually a diamond, it would be about 10 to the 31 carats. So that's a 1 followed by 31 zeros carats. And the problem right now is they haven't been able to design a setting, a suitable setting for something that massive, kind of a little body. But anyway, the largest diamond, I should note that the largest diamond known is not the Hope diamond, it's actually the Jubilee diamond, which is 546 carats, which is pretty massive for a single diamond, but nothing compared to this diamond star that we are just talking about there for a moment. All right. Okay, just want to briefly review again the idea of eclipses. We have eclipses occurring when the moon either passes through the Earth's shadow or when the Earth passes through the moon's shadow. And they would be a monthly phenomenon if it weren't for the fact that we have a tilted plane of the moon's orbit around the Earth. So the moon's orbital plane is tilted with respect to the Earth's orbital plane around the sun, and it's that 5-degree tilt that causes eclipses to happen only rarely, not every single month. If it weren't for the tilt, we'd have a lunar eclipse and a solar eclipse every month. There's another funny coincidence about this whole eclipse business, which is that the angular sizes of the moon and the sun are almost exactly the same, which is about a ½ degree. That's strictly a coincidence. There's actually no physical reason why the moon should have a similar angular size to the sun. I mean, it's all a matter of distance, right? If you go farther away from the moon, it looks smaller. But at our distance from the moon's much, 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 much smaller. It's like about 400 times smaller in radius than the sun, but it's so much closer, again, about a factor of 400, that you just get this coincidence of angular size, which is what gives rise to the solar eclipse phenomenon. So again, we have this tilt of the moon's orbital plane around the Earth, and this 5.2-degree tilt then makes the eclipses relatively rare. We get new moons and full moons every month, but we don't get eclipses every month because of the tilt. When they tilt, we get a solar eclipse every time it's a new moon, and we get a lunar eclipse every time it's a full moon over here. It will look like this every single month. Eclipse, eclipse, eclipse. Okay, so again, so the main thing for us is that there are seasons of the year, there are times of the year when eclipses will occur that we call eclipse seasons. And those are dictated by the geometry of these two planes. Because two planes, when they're not parallel, will intersect at exactly one line. And that line is called the line of nodes. And the line of nodes is the line that the sun is always on that line. The Earth is only on that line during eclipse seasons. Otherwise, it's not there. It's somewhere over in these regions. So we have to have the Earth on the line of nodes, which means we have to have eclipse season in order for an eclipse to occur. That's a necessary condition, but as we say, it's not a sufficient condition. You don't think about logically. Because we have to have eclipse season, which means the Earth has to be on the line of nodes. But if we don't actually get a new moon or a full moon, like here, the Earth is on the line of nodes. It's eclipse season, but it's not a full moon or a new moon. So even though we have the potential to have an eclipse, we don't actually get one because it just doesn't have to be a new moon or a full moon. And if we, here we have everything lined up perfectly and we actually have a full moon, so this would give us a lunar eclipse. And this would be a new moon, this would give us a solar eclipse because we have all the conditions satisfied to do that. Okay, so again, during the solar eclipse, the normal yellow disk of the happy sun is completely blocked out. And what we actually are able to see is a super hot corona, which is millions of degrees. Again, it's so hot that it mostly radiates harmful ultraviolet radiation, which is why it hurts your eyes. But we're not sensitive to that, so we can stare at that all day long, and we're not going to blink because our eyes aren't sensitive to that radiation. We don't even know that our cells are getting burned by this ultraviolet. So that's why staring at solar eclipses is so dangerous, because there's no natural instinct not to do it. So you do it, and you can get really hurt by that. Talk more about that outer structure of the sun later in the semester when we talk about the sun. Okay, so sort of got about this far at the end of the last lecture. We started talking about the size and shape of the different regions of the sun's, the moon's shadow on the Earth during a solar eclipse. So because the moon is so much smaller than the Earth, only about 25% of Earth's radius, the shadow thrown by the moon is a pretty small shadow. It's only a few hundred kilometers across, 270 kilometers across. And that region of totality is called the umbra. So it's a classic question I can ask you about, where do you see a total solar eclipse? Would be in the umbra, the center point. If I say, where do you see a partial solar eclipse? It's in the penumbra, which is that outer point. In that outer gray circle, you see a partial solar eclipse because you're still going to see part of the sun, right? You're still going to see part of the sun sneaking over the top here, or sneaking underneath on the bottom, in that case. So in the penumbra, we see a partial solar eclipse. And solar eclipses last about 7.5 minutes. We'll talk a little bit about why that should happen, why we would have a certain amount of time associated with the crossing of the shadow. Okay, so again, umbra, center point is just above the last image. Penumbra, the outer point, where we see the spot on the Earth. So this is actually a shadow taken by a photo from Skylight, which is an old orbiting NASA from the 1970s. To actually see the shadow, I think this is the first time the shadow was actually seen from space. Okay, so the lunar orbit is actually not a perfectly circular orbit. It's an elliptical orbit, which means that the distance of the moon from the sun, from the Earth, varies slightly during the month, which is this 27.3-day cycle that we talked about just a minute. Okay, so here we have a situation where we have a solar eclipse, but the moon is at its maximum distance from the Earth. So we have a slightly smaller size for the moon, slightly smaller angular size. It's a little less than half a degree. The sun is still half a degree basically all the time, because the Earth's orbit is not very eccentric at all. But the moon, being at its largest distance, is a little too small, so it's a teeny bit less than half a degree, so we see this annular eclipse phenomenon. So this figure just kind of summarizes the different types of eclipses that we can get. We have the annular, again down here, as I just explained. So we have, it's an eclipse of the sun. But if we think about the shape of the moon's shadow for the annular eclipse, there is no actual umbra. In other words, there's no point at which the moon's shadow actually touches the Earth. The core of the shadow does not touch the Earth. So you wouldn't see a total solar eclipse unless you're floating around in space inside that shadow. Okay, so again, there's just a penumbra. So for the annular eclipse, there's only a penumbra. And up here we see a classic, this is actually a case where, again, because it's not perfectly lined up, we don't get an actual total solar eclipse, but we do get a partial eclipse way up in the northern latitude. Okay, total eclipse here, again, because the penumbra actually intersects, the umbra and the penumbra both intersect the Earth. Lunar eclipses are seen from anybody on the night side of the Earth. So, billions of people basically will see a lunar eclipse, whereas only maybe thousands of people will see a solar eclipse at a given moment because the entire night side of the Earth is going to be able to see the lunar eclipse, and it lasts a lot longer, about 100 minutes, so about an hour and a half or so for a lunar eclipse. We'd also have this funny reddening that occurs during lunar eclipses because what happens is, although the moon is in the Earth's shadow, there's a little bit of light that gets refracted or bent through Earth's atmosphere, which acts kind of like a lens. And we have a little bit of red light actually makes it through, gets scattered, and illuminates the moon. The blue light is removed from the beam to create our nice blue sky, a process we'll talk about later in the semester. So the blue light doesn't make it to the moon, but the red light does, and so we can see your moon. So let's talk a little bit about the direction that the shadow would actually move. We're just going to focus on a solar eclipse here. So there's two things that actually happen during a solar eclipse that are going to dictate how the shadow moves across the Earth. One is the moon is orbiting counterclockwise, and we're reviewing this from the north celestial pole. So we have that good old counterclockwise motion. The moon is moving counterclockwise, and the shadow is going to strike the Earth. So it's going to strike the Earth on the western side and move to the east. But that actually depends on how fast the Earth is spinning. Think about it. If the Earth is also spinning counterclockwise, if it spins counterclockwise fast enough, you can actually have the shadow go from east to west on the actual continent of the Earth. There's two things going on here. So I attempt to animate this thing a little bit here. So we have the Earth spinning and the moon moving there. All right, so, and this is sort of roughly accurate, although the time is obviously vastly speeded up here. But the idea is that the orbital speed of the moon wins. and the Earth is spinning slowly underneath, but it's not spinning fast enough to keep up with that shadow. So basically, the upshot of the whole thing is that the shadow of the moon actually moves from west to east. Like right there across North America, it moves from west to east. So the shadow track of the umbra itself actually moves from west to east during a solar eclipse. And I will be asking about this, by the way. And we can even compute the speed the shadow moves. It's about 1,700 kilometers per hour. So the shadow is kind of whipping along there. And its size is 270 kilometers, so that's where you get the 7.5 minutes. Now, the spot's about 270 kilometers across, moving 1,700 kilometers an hour. If you do the division, you get about 7.5 minutes that, from start to finish of the shadow being on you, at most. It might miss you entirely, or it might just slightly vary where you are at. Okay, so again, I will be asking about this. So the idea is that the eclipse actually will start at sunrise in the west because it's a solar phenomenon. So when the sun just grazes the edge here, that would be sunrise on the western limb of the Earth there. And it moves from west to east at 1,700 kilometers per hour. So the thing that wins is the orbital motion of the moon. That's faster than the spin of the Earth. So we get the motion from west to east. These are just examples of solar eclipse tracks from the book. There are some historical ones like 2002, 2005, 2009, and then there's some coming up here like March 2016. Again, the path will start here and move to the east. And we're actually, we're over here. Okay, so in a couple more years, will be our next opportunity to see a total solar eclipse. The red lines are the total lines. That's the total solar eclipse that came to North America. And then the blue lines are the annular partial eclipse lines. But all those tracks start from west and go to east.